Hi, Ron.
Hi, Stefan.
So today I want to present you the progress I made since we started a few weeks ago with the implementation of the distribution libraries. Then I've made the first step in also using the MeshWeaver framework, but I still was running some charts in the console application, and I said I want to implement and to visualize these things inside of the MeshWeaver. And this is what I did. I'm not exactly where I want to be, but I think we made already quite a big progress. So we have now all the distributions are implemented in the layout areas. We can look at individual distributions. We can also compare them. So this was basically what I want to demonstrate today. So this is the topic. If you look here, what we implemented, first we started with taking distributions from the MeshNet library, and what I have listed here is a couple of distributions which we are using. We don't use all of them, but just a selection. And I grouped them, so depending on this underlying support. So we have some distributions which are defined on the support from -infinity to +infinity, like the scaled beta distribution, which you can move along the real axis from wherever you want. Of course, outside it's then zeros. We have the Cauchy, which is a very special distribution, which you can use maybe for certain processes, but it doesn't have a mean, it doesn't have a standard deviation and the like, so it is kind of an outlier. I have it implemented, but I'm not going to expose it. Then we have a continuous uniform, which is also similar to the beta scaled, has a uniform distribution within a minimum and a maximum range. Then what we have is the logistic and the normal distribution. So these are the ones on the full real axis. And then we have many distributions which are defined on the positive real axis. These are also the ones which are important for things like severity, sampling, and the like. So we have here a longer list. And then we have also some special distribution like the beta distribution, which is defined on the support between 0 and 1. So which also used in certain cases. Then similarly in the case of, so these are all continuous distributions. We have also the discrete distributions from the library. And here I've selected the discrete uniform, which is similar to the continuous uniform, but of course confined by integers. Then we have the binomial, the negative binomial, and the Poisson distribution. And these three distributions are all part of the so-called Penger class. So there are special cases. The binomial has a variance to mean ratio of smaller than 1. The Poisson has exactly 1. And the negative binomial, the ratio is +1. So this is how you can differentiate between the three. In some cases, we also need the categorical distribution. And what I've also implemented, which is also an interesting case, is the logarithmic distribution. So we will have a look at them later. And then, since we are talking about reinsurance, there is also a need to have additional distributions. And what I've implemented here is what I call the continuous discrete, which is basically if you have a sample or some discrete numbers, whatever it is, you can generate it with another distribution, or you have an empirical distribution, whatever it is. So basically it creates then a continuous discrete distribution, which means the CTF, the cumulative distribution function, is a step function. This is more or less what it is. Then a special case of it is a Dirac delta function, which is simply one step. You can define the location, there it jumps from 0 to 1. And then we have some other distributions which are not typical for reinsurance context. One is a so-called Maxwell-Boltzmann-Bose-Einstein-Dirac distribution, and there we have two versions. One you find here, the unlimited version, which is defined for the positive real numbers. And this can be used similar to what we have here, the mixed exponential or mixed US Pareto distributions, for instance, for long tail business where you have, or if you have a limit profile and not a risk profile. So basically you have claims which can go up to an undefined value. So there's no upper bound, like in the case, for instance, in the property risks. So this is where we can use them.
Maybe I think also something that many of our viewers will probably not know is that it was actually you who brought these physical distributions into reinsurance, right?
This is in 1997, so it's a while ago. But then the focus was, I mean, I invented them, I defined them, or used them, started to implement them about 35 years ago. But then I used primarily the limited version of this distribution, which I used to approximate what I've mentioned here are Swiss recurves. So these are tabled probability distributions. And I said, why should I only have curve number 1 or number 2 or number 3 or number 4? Maybe in some cases I want to have something in between. So I want to have a continuum. So then I've found a way to approximate these curves with the help of this class. And then, so basically I define the parameters B and G as a function of C. And the Swiss recurves are exactly special cases of this limited MBBF distribution, where you have only one parameter, it's the curve parameter C, but behind it then creates this MBBF limited distribution by telling, okay, what is the B parameter and what is the G parameter as a function of the curve parameter. So this is what I have here. Yes, that's the background.
Yes, and I think almost everyone who works in reinsurance pricing has read this paper. It facilitated my work a lot at the beginning at Swiss Re because we wanted to fit these distributions, and with Swiss Re curves it would have been very difficult to fit. And I was actually super happy that you had written this paper, and I read it, and it was before you were my boss actually, and I had read it and I loved it. And also coming from physics, I had an immediate love for this kind of paper.
Okay, so this is on the continuous side, and we have also some discrete distribution. So of course, again, a sampled version. And then I have the Panzer distribution, which is basically one distribution which includes what we mentioned before, the binomial, the Poisson, and the negative binomial. But here you can specify it by giving the mean and the ratio of the variance of the mean, and then it automatically decides in the background which one it's going to take. So these are the distributions. Then we have quite several methods and statistics which are defined in the MetNet library, and we've basically taken this statistics the same, so with the same terms. So basically it maps it one-to-one, and what we've built is an interface, one for the continuous distributions, which we call here the severity distribution, but it basically covers the continuous distribution in the MetNet library. And here are all the methods which we have implemented. You can find the ones which you've seen above. So all this here. But there is some extra stuff we have here. So what we have here very specific is an exposure curve, which is basically the integral of the CDF. Then what we have also some methods which are used to modify the distribution. So you can either scale it, or you can shift it, depending on what type it is, or you can distort it. And the important thing here is, this also I had to learn from you, Roland. I should not go and modify the distribution itself. It should be, once you have defined the distribution, it should be immutable. But what it does, I call it controlled genetics. So basically, I tell the parent distribution, give me a child which has this and these properties. Yeah. So basically, I can tell the parent, give birth to a child which has blue eyes or red eyes or whatever I want. Yeah? So this is basically how it's implemented. With this, I have both in one. I can use a method which generates what I want, making sure that the parent remains untouched. So I think this should make you happy.
It does.
Good.
We will speak a lot about also cloud-native programming, and these patterns are very necessary if you want to compute in the cloud.
So here you can see this is now for the frequency distribution, which so the discrete distribution, we call it frequency distribution, just to differentiate. And here more or less the same methods. Of course, the density is replaced by the PMF, so the probability, but otherwise it's more or less a one-to-one. And then, of course, what we put is some kind of wrapper around the MeshNet distributions to basically to shield them, which allows us to correct some issues which we find, but also to implement additional functionality as required. And now what I want is to show how this looks like if we visualize the distributions. Here, let's start with an overview. So here we are in the layout area, and here we have different icons, which is work in progress. So basically this, or sometimes this will be looked differently once we roll it out, yes. We don't know yet exactly how, but we basically put the videos behind these things. But what we have here is now here the severities, which we want to compare. So what you see on this screen is all the distributions which I mentioned before. Let's first just show an overview. So here on the top, what we see here is basically if each distribution has a method called toString, which then tells what it is and the parameter. So this is what we see in this area here. Then if we go to the right, so then we have the different statistics. So the mean, of course, which is the most important one, which is what we specified here, so I can change it. I mean, this is now the MeshWeaver framework. As soon as I make a change here, so I change the mean, then you have seen the parameters are updated, but also the statistics here. So this is the magic happening, because we have here the user interface where we basically enter the parameters. Maybe Roland, you can explain what's happening in the background. Then this goes to the business logic, which then executes it, and then it sends back the results, and then the results are rendered, right?
Yes, I would say let's do a dedicated video, but this is obviously a very, very subtle thing in all these UIs, that when you try to do this proactively, when you say, when I change this, then this should change, this is doomed to fail. So you really need to have a different way of approaching it. Let's do a dedicated video on this. I promise it will be one of the next ones. And then we can really learn how this kind of functionality can be achieved.
But the important thing, it works. And what we have here, of course, we can also change other parameters like the coefficient of variation in this case, or I can change the number of samples. But then sometimes you also want to have a graphical representation of the distributions. And what we've implemented here, you can just click the radio button. And what we have now are densities, but these are now not PDF directly, but it's basically bint densities. Yeah, so we define bints and we look at the average density within each bint. So just to make it easier, also in the case of discrete distributions, to basically use the same layout. And what we can also do is, you can go here, but here it's not so visible. We have to do it in a different place. So let's move on. Let's look at the CDF. And here, what I can do is I can then turn on and off certain distributions, you see, to find out which one is which one, because otherwise it's a little bit messy. What we have here is then the cumulative distribution, now just to compare the different ones. Then I've also implemented the survival function, and here I'm using a logarithmic scale for the survival function, which tells us, or gives us an idea how these distributions look like. And then what I've already mentioned is the integral of the CDF, which is the exposure curve. And don't be surprised, it can be negative, yeah, because this is if the support goes also to the negative numbers, then you get here at this point a negative value. So this is just to compare, but of course it's a little bit messy if you want to look at one individual. So for this we have a different approach. Let's look at the Pareto distribution. Again, we start with the tables, and what we've done here is something different. I have a model which is determined by these parameters. So I give again the mean and the CV. The tool then provides then the scale and the shape parameters, and then it provides again the statistics. What it also does, it shows here in numbers the cumulative distribution, so evaluated at these support values. So it starts with the minimum value, which is basically the scale parameter. Then what it does is it takes the distribution and it takes a certain number of samples, so which we have specified here. Then it shows the same statistics for the sampled distribution. And then in the next step, it comes up with a new Pareto distribution, which is taken from the mean and the standard deviation of the sample. So basically, it fits a Pareto distribution to the sample. And what we hope is that the estimated distribution is not too far from the model distribution. Now, if you look at the numbers, this seems to be the case, but of course, we can also visualize it. So here again, we have this Bind probability density function, which doesn't tell too much. So let's go to the CDF. And here we can already see, so the sampled distribution is shown with bars, and the model distribution, which I can turn on and off here, or the samples, which I can turn on and off, and estimated, so the fitted distribution, they're shown here as straight lines. And you see the two are very close. The same is the case if I look at the survival function, so I can resample, and sometimes, of course, they deviate depending on the sampling, but normally they're pretty close. And don't forget, this is a logarithmic scale. And the same also with the exposure curve. Again, the two curves are relatively close. So this is what we have here. So the visualizer or the explorer, we can do the same with, let's take here another example. We have the limited distribution, so the ones which are defined between 0 and 1. We have the beta distribution. Let's have a look at it. So here you have a concentration of the probability at 0 and another one at 1, depending on the two parameters. It's on the one side or on the other side. We can also look at the CDF, where you see the same happening. The survival function, of course, this is in the logarithmic scale, so it looks big, but actually you have less mass on the right side than on the left. Again, the exposure curve, or we can go and look at the Swiss Re curve. So what we have here is, again, it increased, but then we have a total loss probability, which is reflected at the end. So it doesn't continue to infinity, but it's then basically, you say there is an upper limit for the possible losses, and that's why it goes from 0 to 1, and then you will then scale it with the insured value, for instance, or another measure. And there's a certain probability for having a total loss. This is what you can see here. And if I choose a different curve, so if I increase, so now the scale continues to draw beyond, but basically it stops here at 1. This is just also an artifact that the plotting doesn't really stop at 1, but basically something which, of course, it's a work in progress. So these are, let's say, cosmetic things which we can adjust, but the important thing is that we can see what the distribution is doing.
By the way, what I also did over the weekend, because I make you present this in dark mode, because I learned that YouTube doesn't like light mode. And then I saw we had this dark gray color, because I don't think we had even a dark mode in our previous software stack. So what I already did, you don't have this yet, but on mine it's already there, is that I changed the dark mode layout, that it brings now white ones, etc.
Okay.
So this is already done. But this is also going into this build in public, and this library comes from our previous stack. It's Chart.js, by the way. It's an open source JavaScript library, and we just wrapped it, and comes from our previous stack. So it can be that maybe there was also a bug with the axes, and we just need to take them out. Yes.
Yeah, I think this is, as we said, I mean, we are working here and implementing, and as we move along, we will find out what we need to adjust. So this is basically the stage where we are right now, and in a week or in 2 weeks from now, it will already look different.
Yes, which I think is also interesting for our audience, because they can see how we think, how we work, and maybe learn also for themselves how they can approach problems.
And then now what I want to show is something which is not yet working perfectly. So, but I think this is where you can then help to fix maybe some potential issues we have there. But the idea which I want is to have a different approach. Basically, I want to have one layout area where I can select between the different distributions and then do whatever I want to do. So here I can run for the beta distribution. I can also display it. But as soon as I go, and if I select a different one, then it still keeps the beta distribution. You see, we have only 2 parameters here. So and for the scaled, I should have 4 parameters. If I go to the Dirac delta, I have here, it works. I have only 1. But if I go back to beta, yes, now it works. It's sometimes...
Well, we drafted it very, very quickly, right? So we were sitting in a coffee and we drafted it quickly. And so this is also in the next video that I'm going to do. I just, it takes sometimes a bit of peace and quiet to think about things.
But this is basically what I would like to have. So basically one layout area with an interface where I can select between the distributions, then enter the parameters, and then it renders whatever I want. So then I don't have to go to multiple icons and then see where is the one I'm looking for. So this will be the goal for the next step.
Yes, and I promise that this will be the next video, so we can also link the next one already in here and link back. Because I'm in the next video, I'm exactly going to show how we can implement these mechanics to bring this kind of view to life.
So I'm looking forward to it, Roland. And also for the audience, I hope that you're also interested to see what is happening here. So thanks for watching the video up to here. Don't forget to click and to subscribe, and happy weaving.